Swayam Prabha. Digital India. Educated India.
Okay, so I am Mangalsundar. I'm in the chemistry department here. So I'm a physical chemist, meaning that I teach basically fundamental physical chemistry like quantum mechanics, spectroscopy, and statistical mechanics, thermodynamics. These are all subjects which are extremely important for both chemists and physicists, and of course they are fundamental for all engineering and technology. Chemists are always worried about atoms, molecules, and the transformations between them. Okay? So you make molecules, you break molecules, you try and understand why some molecules form, why others don't form. How do we make them? How do we make them form? Find the conditions. Sometimes we bring in external agents like catalysts and whatever that you can. Idea is today to make molecules with specific properties. About 150 years ago, the idea was to make molecules. Okay? There were few molecules, therefore everybody tried to do something. And then they realized that the properties of molecules and atoms unfortunately do not follow the properties that were very well known until that time, namely the changes due to changes predicted by classical mechanics. Molecules cannot be studied, individual molecules cannot be studied purely by methods that were known at the time. And the most famous example in those days was, you heat sun, radiation coming from sunlight. Radiation coming from the hot light emission of hydrogen atom, for example, heated to 6,000 degrees or 5,000 degrees. Those radiations, if you try to understand when they are captured, you found lines rather than absorption by the atoms, all of the energies. So that was the beginning of what they call as a spectrum. From that point onwards till today, we know that molecules cannot be studied using classical or well-known physical methods, but you have to go to the new mechanics. It's no longer new, this is the 100th year, the new mechanics known as quantum mechanics. Okay? Study of molecules and atoms. The most appropriate way of doing that is using quantum mechanics. But when we say quantum mechanics for studying, what do we mean by studying? What do we mean by that? After all the physical chemists were doing experiments. And they are doing experiments even today. And a large majority of them don't need to know quantum mechanics. Okay? You want to measure the vapor pressure of water. It's not a chemical property, it's a physical property. But something else, you heat something and it decomposes, you measure the energy that comes out of it, called enthalpy of a chemical reaction. or internal energy changes in a chemical reaction. Whenever you study things in bulk, when large molecules are involved, it looked like we do not need the details of quantum mechanics. We could study them using what we call as macroscopic methods for studying bulk properties. For understanding bulk properties. Behavior. However, if you want to know why a molecule absorbs light or emits light, and under what conditions does it do, and how many different forms of light does it emit, if you want to know those details, molecular level details, not Avogadro number of molecules sitting together and giving an average property, such as, the reaction enthalpy or free energy. I'm sure you have heard these things in your classrooms. Those are what are called the bulk behavior, bulk properties. We don't seem to need so much information about how the molecule is studied using quantum mechanics. But then, when we want to study microscopic properties, microscopic. Example. What is the structure of the molecule? Precise, not approximate. Precise structure. Three-dimensional shape of the molecule. Electric properties of the molecule. Magnetic properties of the molecule. Spectroscopic measurements, which involve both of these. And many others, if you want to write down, there's a whole list of things. If you want to know all these things, you need to study quantum mechanics. I'm sure in your 11th standard book, there was a chapter called Atomic Structure, right? So you studied something like the photoelectric effect. All of you did that. That Einstein was the first one to explain the phenomenon of photoelectric effect, namely some metals, when UV radiation falls on them, emit electrons, but the same metals, if infrared radiation falls on them, doesn't emit electrons. So the photoelectric effect, the emission of electrons due to light photons falling. Einstein's theory, I'm sure you would have seen that. And before that, probably something called the black body radiation that Max Planck came up and tried to explain, which could not be explained until then by many others. And then you also know the story of Niels Bohr coming up with the electron going around the nucleus in spheres, in spherical orbits, and so on. Okay. And if all of this is not enough, then came 3 people or 4, 5 people, you can call them whatever that may be, but number of people came in and said all of these things are okay, but there is a fundamental property, fundamental behavior, and that we call it as the modern quantum mechanics. And the persons who discovered this are 2 very famous people. One is Schrödinger, the other one was Heisenberg. They both came up. They didn't study chemistry, they studied the atomic properties of the spectrum of the atoms. They tried to understand that. And then, of course, came chemists who saw the validity of these things and then tried to understand a molecule using the same model. We haven't finished yet. It's 100 years now. Okay? We are still learning. from that. That's the microscopic level. Okay. But for macroscopic, you want to measure thermodynamic properties. Okay. Enthalpy is a very famous example. Internal energy change, heat capacity, and whether a substance has free energy when it undergoes a chemical reaction, whether it releases energy outside of these mechanical energies, outside of thermal and mechanical energies, it releases free, so-called free energy. And what are the conditions for a chemical reaction to take place spontaneously? All these things are done in bulk. So, as a class, I can get an average behavior for the 40 of you. Okay? And if I go to a football stadium as an average of maybe 40,000 people, we can get some behavioral patterns. And those are what we call them as the bulk or the macroscopic behavior. What an individual does is usually irrelevant for that crowd. Okay? So if you are looking at a bulk sample, for example, 18 grams of water. There's nothing special about 18 grams. It has 1 mole of water. Okay? 18 grams of water contains 1 mole of water molecules. And 1 mole is what? 6.022 10 to the 23. The world's population approximately today is 8.5 or 9.5, I don't know, depending on which, into 10 raised to how many? 10 raised to 9 billion. Billion. 1 billion is equal to 10 to the 9. So this is what? 10 to the 14 times billion. Okay. It's almost, since it is 8.5, it's almost 1 billion million. No, it's not even, 1 billion million. 10 to the 9, 10 to the 6 is roughly 10 to the 15. So 18 grams of water represents individual numbers, if you think about it, individual molecules, if you think about it, is way, way beyond the world's population. Therefore, even if we want to know what an individual water molecule does, and we want to follow that, it's very difficult. The reason is 18 grams of water is about 18 ml, small, very small volume. This may be this much. And no matter how big a microscope you have, you don't want to study what a water molecule does individually. You know, how do you study that in case you want to study? There is a branch called molecular dynamics. In that branch, it is a computational study what we do. We tell the computer that in this volume there are these many molecules and this is the interaction energies between them, and here is a starting condition. These are the equations of motion. Let the computer calculate what happens in the rest of the time. That's molecular dynamics. The most that the molecular dynamical calculation can do about a few years ago was to study about 1 million such molecules in a small volume. Not anywhere near this. Therefore, average properties of molecules are extremely important for us to understand and make use of them. See, when you say water is at 100 degrees Celsius, what does that actually mean? Or when you say water is at ice is 0 Celsius, what does that actually mean? When you say temperature of the system is this, what do you understand by that? Yeah, louder. What measurements? What do we measure? Yeah, some measurement, but what do we measure? Average kinetic energy. Yes, that's one example. That's a good example. Kinetic energy. What is the average kinetic energy corresponding to this temperature? So you can say that the molecules have higher average kinetic energy if the temperature is higher. If the temperature is lower, the molecules are moving with a lower speed, lesser speed, and therefore they have a lower kinetic. One example, typically, approximately this is right. But temperature by itself is not a property of the system. Temperature is a measurement interpretation that you make. The property of the system is the kinetic energy. The property of the system is the velocity. Every molecule has a velocity of motion above 0 Kelvin. Okay? 0 Kelvin is the lowest temperature when molecules come to rest, but they don't. Quantum mechanics tells you they are not at rest. They are at rest in the sense they are located, but they are moving among themselves due to some local vibrations and so on. So quantum mechanics has very strange results when it comes to very low temperatures. So by temperature you mean something, but temperature is something that you cannot define in quantum mechanics. Temperature comes out because of the very large number of molecules coming together, and you see the perception of a heat content in the system. Okay? If the system moves very fast within a local volume, then it has more energy. And therefore, to touch it, you feel it's hotter. Okay? So, perception. Your perception of a higher energy or a lower energy or higher temperature or a lower temperature is based on your response, the system's response to you. So, macroscopically, you can say some things like that. Temperature is one example. The pressure of the system. What do we mean by the pressure of a system? Yeah. Force per unit area, but what is the force and where is it and how does it come in? Pressure is always due to a confinement. The confinement tells you that the molecules are hitting the walls. Okay? And they are hitting the walls, their momentum keeps changing. The rate of change of momentum is equal to the force. Okay. When you calculate that per unit area, you say it is a pressure. So pressure is a mechanical property because you're talking about momentum, mass and velocity. Pressure is something that you can talk about, but pressure is not about the individual rate of change of momentum. It is what the walls experience on an average when millions and billions of molecules are simultaneously hitting the wall and coming back. If they hit it faster, harder, obviously the pressure on the walls is higher. Again, it's a bulk property. Even though it is a mechanical property, pressure P, even if you say it is a rate of change of momentum per unit area, when you measure, say, atmospheric pressure or 1 bar or 2 bar pressure, it's an average property. We average over so many millions of collisions on this one. Volume. What do we mean by the volume? The region to which it is confined. The system is confined, okay? Which you don't have to worry for a solid because the solid has its own volume. The liquid usually has finite volume, but it takes a larger surface area if you provide more area. The liquid spreads thin. The gas, on the other hand, all volume. Whatever volume you provide, the gas occupies all volume. Okay? So volume is another example of a bulk property of a larger number of molecules. So these are quantities which are useful to understand roughly in equilibrium what the properties of the molecules are, the energies of the molecules are, and the work that they do when they expand a piston, or the work that is done on them when you push them with the piston on top in a small volume. Or what you do, you heat water in a small beaker but completely cover it you see after some time the beaker will crash, will break open. Why? The pressure will eventually make sure that the glass cracks. Okay? So the pressure builds up. But these are bulk measurements. On the other hand, for example, this blue color, what is it due to? Every one of you is wearing a colorful shirt, including me, of course, yes. What is the color due to? Does a photon have a color? Does a photon is light packet, does it have a color? Photon has only one property. What is it? Sorry? I didn't hear. What does it have? Frequency, yes, yeah. Photon has only one property. Frequency. Doesn't have color. But we give color to that. To this one, to this one, to this one, to every one. And then there are lots of photons here without color. Okay. Do we? What are they called? What are they called? Photons without color. Louder. Louder to me. There is a lot of echo, so I have a problem. Yeah. They might be? What do you normally call these photons by name? Infrared photons. Ultraviolet photons. Okay. This room is full of them. Your body emits infrared radiation because you are at a finite temperature. All of you are at 37, 38 degrees Celsius, 36 degrees Celsius. Any body which is above 0 Kelvin will definitely emit a small amount of radiation. So all of you emit infrared radiation, but you don't realize. So light, for example, when you talk about the property of color is of course a perception and the bulk property, and there is a very narrow range of the properties of light that lead to color. The narrow range is 300 nanometers to roughly about 800 nanometers. That's it. In that range, you see light with color. The rest of the region, you don't see color. Atoms and molecules constantly interact with light. They absorb light. And they emit light also if they are hot. And this color is obviously due to the fact that whatever the molecules are here, which are absorbing the radiation, they are emitting what? They are absorbing the complementary color. And so what you see is the color that is transmitted. Okay? So every color that you see is the color that is complementary to what is absorbed. But if the object is black, what does that mean? It absorbs all colors, no emission. If the object is white, what does it mean? It emits all colors. It emits all colors. Okay? So this is another side of the story, that atoms and molecules are constantly interacting with the universe, but only through light, largely. Light in the sense, all radiation. Light is no longer visible or color light, but electromagnetic radiation. Now, to study that, you cannot use any of these bulk methods, electromagnetic radiation. Okay. Plus matter. The interaction between electromagnetic radiation and matter is what we call as spectroscopy. There is only one way to learn this very well. You have to go with the quantum mechanics. There's no other method. There are semi-classical theories of light, absorption, etc., etc. But to understand the fundamental properties, suppose you want to study all these things from the spectroscopy, from the interaction of radiation with matter, you have to use what is called spectroscopy. Okay? And today, of course, chemistry, physics, engineering, hospitals, everybody uses spectroscopy, okay? Everyone. And the properties of the magnetic properties of the molecules can interact with the magnetic component of the radiation. You know, when you say electromagnetic radiation is oscillating like this, okay, when you say that this is the propagation direction, you know that it is also oscillating, right? What is this? Suppose this is the electric component. What is the other component? That's the magnetic component, yeah. So electromagnetic radiation is basically the unification of the electrical properties and the magnetic properties that we know of matter. So electromagnetic radiation has both of them. When the magnetic component, for example, interacts with matter through the magnetic properties of the matter, then we get what is called magnetic resonance spectroscopy. When the electric properties interact with the electrical properties through absorption of radiation and emission, and we get the signatures of what is actually happening, that is called optical spectroscopy. It's not called electric spectroscopy, but it's usually called optical spectroscopy. So we do have that. Both are quantum mechanical, understood. Both are resonance spectroscopies in the sense the radiation that is absorbed has to be very precisely matched with some properties of the molecules. And the properties of those molecules which are important are the energy levels of the molecules. The energy level should have sufficient gaps, and the radiation must match the energy level difference between a given pair of energy levels. That is spectroscopy. So you have bulk chemistry, you have laboratory chemistry, and then you have the atomic and molecular chemistry. You also have laboratories because spectroscopy is all done in laboratories. And then you have molecular simulations and modeling of how the bulk behavior can be understood from classical equations of motion, from quantum mechanical equations of motion. How do we program this? How do we create initial conditions for studying this? That is molecular dynamics. All of this is physical chemistry. Okay? All of this, the study of all of this. But there is a study called chemical physics, which is not play of words. You know, physical chemistry and chemical physics are not play of words. They are very, very clearly, beautifully defined areas. Physical chemistry studies generally bulk properties. Through thermodynamics, through chemical kinetics, through catalysis, through surface science, even measurements, quantitative measurements, all these things, they are all studies of bulk properties. Physical chemistry laboratories constantly do that. Chemical physics, on the other hand, tries to study molecules from the fundamental equations of motion called the Schrodinger equation or the Heisenberg's equation or any corresponding transformed quantum mechanical equation. Okay? So this is the general layout that you have, and therefore when you see in your textbooks these things in physical chemistry, you should immediately ask the question, so where does inorganic and organic chemistry go to? Right? Are they physical chemistry subjects or they are standalone subjects by themselves? Organic chemistry, you know, synthesis of compounds and the classification of compounds that you have, starting from alkanes, alkenes, alkynes, alcohols, all those things. Where is quantum chemistry in them, or where is the physical chemistry? Of course, they are systems. You can study those systems using quantum mechanical methods. If you want to know more about why a chemical reaction takes place, and if you want to understand how chemical transformations have happened in the universe so far in nature, you know, with so many minerals there, and you are extracting metals out of them, you are extracting so many other things from them and use them to do your material science. The physical chemistry principles are the same for all of them. But organic chemistry in the laboratory is based on quantitative measurements and observations. You don't really need to look at the spectrum. Today you have to. When you synthesize a molecule, you need to know its exact structure. And you can't get that except through resonance spectroscopy. You synthesize the molecules, you take the sample, go to a laboratory which has a spectrometers and give that to the attendant or the scientist there. And 3 hours later, you get a spectral sheet saying these are the absorptions, so this is this molecule. So organic chemistry, inorganic chemistry, surface chemistry, polymer chemistry, nuclear chemistry, radiation chemistry, everything that you think about, all of them, the fundamental properties that you need to understand for each one of them are essentially in these, the physical, chemical, physical methods and physical chemistry methods. Okay? So that's a reason why you see branches in your textbooks, but rarely the connection between them is brought in. It looks like it is one half of the book and the other half of the book is this. Should I study this or omit this or whatever? You'll ask the question. I think, how many of you will be writing JEE? I guess everybody here? Everybody here, mostly everybody here. So you will worry as much about what is included in the syllabus as what is excluded in the syllabus, because that's the first thing you want to keep it out. Don't want to waste your time learning that, but that's bad. Leaving holes on your carpet, okay? So if I try to pour the water doesn't stay on the carpet. It doesn't heal you. It goes right through. So you can't leave holes in them. And the subjects, okay, all of this, there is biochemistry coming in them. That's another subject. At the end of the day, biochemistry rests on the details of organic chemistry. Every biomolecule is finally an organic chemistry synthesis molecule. Every biomolecule, protein, lipids, carbohydrates, talk about anything. At the end of the day, you want to do that in the laboratory, you must know the organic methods, organic chemistry. So that's a fundamental, just as we say, quantum mechanics is the fundamental basis for understanding the atomic structure, molecular structure, atomic properties, and molecular properties. Organic chemistry is the fundamental requirement for understanding biochemical processes. And surprisingly, organic chemistry will also need the quantum mechanics in order to see if you want to synthesize specific drugs. You can't go to the laboratory and do 10,000 experiments. Your budget will blow off from 1 billion to 10 billion if you start doing that. So you have to know exactly what experiments have to be done to, say, get a COVID solution or to get a solution for any of the viruses and so on. You have to be very focused. The understanding of those things, even synthesis of those kind of systems, finally go back to quantum mechanics. You have to understand quantum computational chemistry. Why computation? Because you can't do the calculations by hand. You can only study silly 200 years now. Still, we have exact solutions for only 4 model problems. Okay. Particle in a box, particle on a ring, particle on a sphere, and hydrogen atom. Everything else, if you want an exact solution and you want to match it with the real life, you have to go to the computers. Earlier, computers were not there, therefore people used to do calculations using what we call as approximate methods. So saying instead of square root 2 as square root 2 as 1.4142. That's because somebody knew enough number of decimals so they could do 1.4142. Otherwise, they would only say the square root of 2 is between 1 and 2, okay, approximately. And then when somebody asks a question, is it between 1 and 1.5 or 1.5 and 2? So you bracket the range. So the approximation method essentially brackets the range of final results. And these approximations eventually became better the moment computers were discovered. Today, the single largest user of computers and computational tools are not computer scientists, are not engineers. Okay? They are chemists and physicists because they study fundamental properties of atoms and molecules using computational procedures. And these procedures have been characterized over the last so many years, and they are all based on mathematical methods. So if we think that we have to learn everything, the question goes back to what I heard as a lecture from one of the Nobel laureates here. This is my story. Please don't take it verbatim. This is how I recall, because I know I'm getting recorded. Likely sometime somebody will look at it. But the way I remember, it was, if I remember, Professor T.D. Lee, who was a Nobel laureate for his contributions in molecular reaction dynamics, along with two others. T.D. Lee was here. So he recounts the story of how he did his research. Okay? He said he went to BSc after his high school and he wanted to study chemistry, probably. And then his seniors told him, you know, you want to understand chemistry, you must also study physics. A lot of chemistry is physical chemistry, you won't know. So he also majored in physics. Okay? And then when he went to MSc for his chemistry studies, they said your physics and chemistry is not enough, you must also know enough mathematics. So he majored in mathematics. And then he goes to US to do his degree, PhD degree. And his supervisor looks at him and says, yeah, you have all these backgrounds, do some research. 6 months later, he says, I've done this, he explains to the research supervisor. And the supervisor listens to all of them and said, good, good, looks good, continue. Another 6 months. After the presentation again, looks good, continue. 3 years. It goes on like this. And then this man gets very rusty, he gets very angry, he says, goes to the supervisor, he said, I want to know, you only say it's good. You never say what's wrong with this, what I should do, why I should do all these things. You don't tell me any of those things. Supervisors told him apparently, when I say it's good, it's largely because I didn't understand many things that you said, even though they seem to make some connections with what I knew. But you came with something different from what I knew. So I said, go ahead, continue. I said that. So now that you have done this for 6 semesters, I think you have done reasonable amount of research, write your thesis and go away. What is important is that there is no one thread of learning that you will stay on. If you want to study chemistry very well, you cannot avoid mathematics or physics. And you may avoid biochemistry because you may say, I'm a core chemist and so on. But if you want to study biochemistry, include 4 subjects now, maths, physics, chemistry, and biology. You need to know biology to understand biochemistry. So threads are there. Science is united. At some bottom level, science is fundamentally connected with all of them. Don't say mathematics is such an ideal, it's a human invention and it's not natural, it's discovered by the human. No, we don't know. There are enough patterns which exist in nature that we need to think about whether science, mathematics was already conceived by nature. So whatever you study in RSIC in the next 40, 45 lectures, about 80 plus, is only an exposure to see how each subject is connected to every other. That's the only reason why you are here. We don't want you to come back and tell us how much you learned and how much you have memorized in writing an exam. I don't want to know any of those things. I just want you to be. Please remember, I was from the very first day, like Mrs. Vijayalakshmi and your other teacher. I've been here since 2009, roughly. Vijay, 2009? Yes, yeah. And so you are about 15th or 16th batch of students. And Bala, of course, was, he's always the opening batsman and he's always the star batsman. So we never question him when he say, I want to open the lectures. Bala will always do that. And it's a fantastic series of lectures he will give. And he will connect large and small. physical concepts with the world. But if you go to other subjects like chemistry, biology, they are not standing alone. They are not in their own pillars. At the end of the day, the basement is common to all of them. Okay? That's where everything, a physicist would have been a chemist to begin with. A chemist would have been an engineer to begin with, studied engineering, and later found that many solutions that he proposed, he didn't understand them. What is the fundamental reasons for that? Would come to chemistry, would come to physics. Many electrical engineers from this institute have ended up doing their PhD in physics because they saw the connection between the basic engineering they studied and the fundamental physics and so on. So the connectivity between all these fields is so strong, but so little visible in your high school textbooks that you have a chemistry textbook, you have a physics textbook, you have a math textbook, and even in math textbook, you have 2 sections of math textbook. Looks like each chapter is unconnected with every other. 30 years later, if you continue to look at these, you will see how they were connected in every one of the things that you did. Okay? So science, mathematics, physics, chemistry, they're all in one stream. There is nothing like one is better than the other. Each one helps the other to build and find more, and it's mutual. Today, to build a laboratory like this, or what you see, you will see a laser laboratory maybe when there is some time. My colleague, Professor Rajkumar, has a beautiful laboratory. You'll see you need a mechanical engineer, you need a physicist, a laser physicist, you need a chemical engineer, and you need electrical engineer, and you need an electronics engineer, and you need a computer specialist. Everybody needs to build one lab. When you have time, go and look into one of the last thing that I was familiar with, femtosecond chemistry. Founder is Ahmed Zawahid, professor, University of California. Oh, sorry, he was in Caltech, California. Institute of Technology, CA, Pasadena. I think he was in Pasadena. If you have looked at his labs, and if you look at major spectroscopy labs, you will see that the subject is not just chemistry or physics or mathematics. The subject is you need experts in all domains to sit together and solve a common problem. Set up a measurement cell that will measure this level of accuracy and this level of precision and these many samples, put down your requirement, and then you build the lab. And the lab cannot be built by one person. Therefore, collaboration between all of you, all of the different domain experts, is what makes today science a great thing. Anyway, before I close today's lecture, when do I finish? Another 5 minutes? 5 minutes, 10 minutes? 5 minutes, okay. The most worrisome topic today for all of you, I mean, there are many, at least the one that I am a little bit familiar with is something that may affect your life. All of you are using computers, all of you are using devices, computing devices, your mobile phones, your iPads, your laptops, everything has computing devices throughout and has PC boards containing millions of circuits and so on, and all of them are called the classical computers. They follow simple law that the atoms and molecules don't interact with each other sitting next to each other. They're far apart. But if you put, instead of 1 million circuits, you want to put in 1 billion circuits. You have to obviously do it in a small board, you have to make it more crowded. And the more crowding you do, the more closely you are bringing all these molecules together. And when the molecules are very close to each other, the quantum effects become very important. Molecules start overlapping with each other. Bonding happens. Van der Waals interactions happen. Polarization interactions happen. Molecules start interacting with each other. So this is today. Tomorrow, already it is on computers, quantum. And they will affect your life because they will do things that you never imagined would be able to do, but they will all do that. Therefore, it's very important that you see the connections that you have in understanding the chemistry. Why chemistry is important? The devices are made of chemicals. Quantum computers are not made out of non-chemical objects. Okay? They are made of elements again, silicon, whatever that you think about. Okay? Everyone is one of the elements. And chemistry has 92 numbers as on date. I mean, there are 118 elements, but 92 elements are common. What is the 92nd one in the periodic table? Uranium. What is the first one? Of course, everybody knows hydrogen. Okay? So there are 92 labels. Mathematics, computer, classical computer has only 2 labels, 0 and 1. Except that you put too many 0 and 1 generators together, 64 processors, 128 processors, 256 processors, then you see you can generate a lot more complexity. And today's entire network, entire computing system, this process is made of ones and zeros. Biology offers 5 letters. A, T, G, C, what's the 5th one? U. 5 letters. The entire genome, the structure that we understand as of now is from these 5 letters, A, T, G, C, DNA, or AU, GC, which is RNA. Okay, 5 letters. So 5 letters make the entire biology understanding, and the bioinformatics that comes out of it is how these things interact, how these things replicate, how these things transfer information. You can think about that. That's a whole group of people doing that. But chemistry gives you 92 of them. Okay, not 1, not 2, not 5, but 92 of them. If you are intelligent and you are sharp, you can find use for elements which were never found to be useful until maybe a few years ago. And the properties of these materials are as uniquely different in many cases as 1 and 2 are. Okay? Even though there is a lot of overlap in properties, say for example, among all the transition elements, all the inner transition elements, F-block elements. But why are they individual elements? Why don't we say one block, one element with different structures? They all have different properties. And it is the exploitation of these different properties to the benefit of building a social order or a social culture or an economic superpower. If you look at it, chemistry offers you a lot more opportunities because we have not understood many metals as well as we would have understood the 5 letters in biology or the 2 elements 0 and 1. What about 0, 1 and 2? What is it called? 0, 1 is usually the binary process. Then you have a trit, 3, 0, 1, 2, such is possible. And you are also familiar with other systems. The one that you use is decimal because it uses 0 to 9 as the only number system. But then you have hexadecimal systems. Those are all theoretical systems. Largely, the most important one is, of course, the binary. And the quantum mechanics, when it goes to quantum computers, it also starts with binary, but with a complex combination of these binaries. And so you see that the physics there, again, goes back to the fundamental quantum mechanics. So in the next 2 lectures that I have tomorrow, I'll talk a little bit about the basic principles of what we call as the quantum, okay?